I'm Sihun Lee from Mahler Lab, Sogang University. Let's talk about leitmotifs. Leitmotifs are musical phrases that represent a character, an object, or an idea in a story. They're widely used in operas, musical theater, film scores, and even video games as a musical storytelling device. We can see one of the most prominent uses of leitmotifs in the works of the German composer Richard Wagner. His operas famously feature hundreds of leitmotifs that are reprised throughout the multiple hours of music drama. And to those who deeply enjoyed the works of Richard Wagner, recognizing and identifying the occurrences of leitmotifs is considered a very important part of the listening experience because it allows for a whole new understanding and a deeper connection to the music. And if we can automatically detect where leitmotifs occur in an audio recording using deep learning models, it can serve as a very useful tool for theoretical analysis, music education, and just enjoyment in general. So, how can we achieve this? Well, the first approach that comes to mind is treating this task as a form of sound event detection, where a model has to predict the activity of all leitmotif classes for each time frame of audio representation. In fact, this is exactly how it was done in a previous study by Michael Kraus and colleagues in a 2021 paper. However, we suggest that it might be more beneficial to take a different approach with this admittedly challenging task. Each occurrence of leitmotif can vary a lot in composition and instrumentation, and often it's really hard to pinpoint what exactly makes a valid instance of a certain motif. So, to better reflect this malleable nature of leitmotifs, it might be more appropriate to represent an occurrence as a singular grouped event rather than a stream of frame-wise probabilities. To do this, we take heavy inspiration from the YOLO family of models in computer vision. These models are used for neural object detection, and they perform regression to predict the position and size of bounding boxes around objects. So we took the different ideas showcased in the different versions of YOLO to build and train a model for one-dimensional time boundary regression. And now we have a model that can simultaneously predict the class and the starting and end points of multiple leitmotif occurrences in a given audio clip, which is more in line with how the dataset is structured. And while it's hard to directly compare this model to a frame-wise prediction model, we see comparable results both in precision and recall. And the added bonus is that when we have a single motif repeating back to back, and this happens a lot, we actually get to see the boundaries between the occurrences. A frame-wise model in this scenario can only output a long, continuous prediction, and it's hard to know where each one starts and ends. Now, our model is far from perfect. It struggles to predict leitmotifs in a completely unseen context. This is a problem also shown by the authors of the previous study, and we think we'll need to take some more groundbreaking measures to get better results, like leveraging models that are pre-trained for other tasks such as automatic music transcription, using advanced data augmentation techniques, or just building a much larger data set. In any case, we hope that our report brings more attention to the intriguing task of leitmotif detection in music audio.